just show you this ideal spring. It oscillates for good forever. There's a damp spring. You can see that every once in a while they stop, and then they get excited, and they start vibrating, and then stop. And that is what we call some people call damp spring, and some people call spring despot. In other words, that spring really has some damping effect. Normally, in mathematically, we describe the damp spring called the spring despot. That means we will have the despot. That's the B here. We got despot here, and that's what we do. Now, the question is, how can we describe this motion in terms of mathematical equations? How can we express this motion using ordinary differential equations or partial differential equations, some differential equations you already learned in your classes. Most of the classes offer in undergraduate studies. So, the next, let us look at the whole tune mass damper. The tune mass damper, here we just show you a very simple, the most simple, the simplest one, the simplest tune mass damper you can ever have. That means we have one spring called K1 there. So this K1 spring, we represent this K1, we represent a system by this spring called K1. And then we have the despot. I need to hide this guy here. Then we have a despot that is here. The despot is the damper. Despot is a damper. The damper includes the mass M2. The mass M2 there, and well, let me use this. The damper includes mass M2, and then spring K2, and also despot C2. So, if you look at this, then, well, let me use this board here, and then I use this guy, and this is the system. Okay, and then this we call the tune mass damper. So we call tune mass damper. All right. So all the simple with subscript 2, we say this is, we define this represent the tune mass damper. Now, what is the second order equation of motion for the whole system here? All right, so that's what I'm going to do, show you. How to use this guy. All right, and now we have two equations. The first equations for M1, X1, double dot equal to minus K1 and X1 plus K2 parenthesis X2 minus X1 parenthesis plus C2 parenthesis X2 dot minus X1 dot. Now you can see that we have X1, that's a displacement of M1, and X2, that's a displacement of M2. And this is the equation to represent the system. The first equation that gives you the motion of x1 in terms of the equations of motion, the second order equation of motion. Then the second equation will tell you what is the x2 displacement. That means the two mass as m2 and x2. So now we have two equations because we have two states. One is x1, one is x2. This is the math. This is the mathematical model that gives you the dynamics behavior of the whole system. Okay, now what can we do about this two equations? How can we solve it? So let's go to next. We also that the converted to first order equation of motions. That means we define the x3, that's our x1 dot. We define another state called x4, that's equal to x2 dot. And after that, we will be able to rewrite the second order equation of motion in terms of the first order equation of motion. Alright? And in your homework, I also ask you to do this. Now there's a question. The question is this the only way to convert the second order equation of motion to the first order equation of motion? Is that true? If I give you a midterm exam, I say, all right, I convert from second order equation to the first order equation of motion. Is this the only one way? Is there only one way? Or any other way to do it? Is there any other way to rewrite the second order equation of motion to become the first order equation of motion? We need to keep thinking about it. Math is only a tool. This equation, the equation of motion, the ordinary equation of motion, is only a tool. Allow us to do what? Allow us to do simulations, or also your homework. I ask you to do the simulations, right? Allow us to do the simulation to predict the dynamics behavior of this system. So, the first order equation of motion, this is, well, you don't give me answers, so I have to give myself the answers. This is not the only way to do it. There are many different ways to write from second order equation to the first order equations. So, if I give you exam problem, I say the first order equation of motion converted from second order equation of motion is a unique form. The answer is no. Alright? So there's many different ways to do it. But this is the most common approach to do it, because this is easier. And this has some physical meaning, because x3 is the velocity of x1. x4 is the velocity of x2. So there's some physical meaning for this. Because most of the people are using this. So the matrix equation of motion now become this way. Now is 4x4 matrix. For this, we call M, we call the mass matrix. Well, it's not really a mass matrix. We call that this is, on the left-hand side is a 4x4 matrix. And then we have another matrix is related to the K, the spring, and damper. That's another matrix 4x4. All right. Now the states, number of states increase from x1, x2, and then we, in addition to x1, x2, we have x3 and x4. So in the first order equation of motion, we have basically 4 states. So displacement is a state. Velocity is also a state. In the first order equation of motion, now you have 4 states. Now 2 states represent the 2 displacements, and 2 states represent the 2 velocities. Okay, that's the mass tempo, tune mass tempo. That's the equation of motion that to describe this tune mass tempo. All right. So it's very simple. Tune mass tempo is very simple, and I will show you. Perhaps I don't know. We have enough time this hour or next hour. I will show you how you tune the mass M2, or how you tune the K2